Hello everyone, welcome to the second part of our discussion on economic section, and in this video we will try to solve an example. So if you were not able to watch the first part of this video where I discussed to you the theory, some of the important theories on how to solve economic section, please do watch. I have provided the link in the description below. Okay, let's try to solve an example. We have here, determine the economical wide flange shape for the simply supported beam if the allowable stress is 18 kilopound per square inch. That is the allowable flexural stress. Now, our first goal here is to determine the maximum moment, because that maximum moment there could give us the stress experienced by the beam. Okay, since we need to compute what should be the required sections given that moment and the allowable stress. Okay, using the flexural stress formula. So again, what we need to do here is to determine or compute the maximum moment. But since this is a simply supported beam and we only have uniformly distributed load across the 8-meter length of the beam, then we are pretty sure that our moment here occurs at the center of the beam or at the midspan. But to prove that, let's try to solve it. It's either by using moment equation or area method. But in this problem, I would prefer area method. Now, we are supposed to compute for the reaction first, but in this problem, we have the reactions already computed. We have the reaction at 1, which is 48 kilonewton, and the reaction at 2, which is still 48 kilonewton, which is correct. So we can sure that R1 and R2 are equal. Okay, since this is symmetrical with respect to the y-axis. So by starting on the left support, okay, so we have our shear there, which is 48 kilonewton. Since that is acting upward, so that means that is positive, and that is locates above the reference line. So we have 48 kilonewton here. Okay, this one we have 48 kilonewton. So that's our shear 1. Then we compute for the shear 2, which is at the right support, since we do not have this continuity within the beam. Okay, so we go directly to the right support. So our V2 here, which is the initial shear, which is 48 kilonewton, minus the area of our load diagram, which is 12 kilonewton per meter multiplied by the length, which is 8 meters. Okay, so we have our shear 2. Again, this one is the area of our load diagram. So the area of this diagram here. So we have our V2, which should be 48 kilonewton. Okay, so let's try to check it. We have 48 minus 12 times 8. We have negative 48 kilonewton. That is negative. So therefore, the location of this shear is below the reference line. So we have here negative 48 kilonewton. Again, this is our shear diagram. Now take note, this is 0-degree load diagram. So our shear diagram should be in the first degree order. So we connect the 2 points. Then we have our shear diagram. Okay. Now our shear 3. Now take note, we have 48 kilonewton at the right support, which is acting upward. So we have negative 48 kilonewton, our initial shear, plus 48 kilonewton, which is acting upward, and this gives us 0. So that means our shear diagram ends with 0 shear. So therefore, we have correct shear diagram. Then let's proceed now to our moment diagram. So since our left support has only one reaction, and that is a concentrated load, so therefore our moment there is equal to 0. So we start with a 0 moment. Then now take note, to compute for moment 2, we need to add the initial moment and the area of our shear diagram, correct? Now, in this case, our shear diagram is this one. So, we need to add the area of the triangle since that is a triangular shape. So, 1/2 times the height, which is 48 kilonewton, and the width, this one. How are you going to compute this base here? Now, take note again, since we have 48 kilonewton here and 48 kilonewton at this point, so we can ensure that the value of this base here is 4 meters. That is half of 8 meters. Since again, this is also 4 meters. If not, how are you going to compute the base width? So that is just basically a ratio and proportion method. Now let's try to do it. Okay? So let's assume na this is x. So therefore, the width here is equal to 8 minus x. Correct? So by ratio and proportion, we could have 48 is to x equals to 48, okay, this over 8 minus x. So this triangle here equals to this triangle. Okay, that's similar triangle. So we have the value of x here equals to 4 meters. Okay, so if you try to solve it using your calculator, so therefore x is 4 and the width here is 8 minus x, that is 4 as well. So let's go back to the computation of our moment 2. So we have 48 times 4, and again this positive since we have positive area because our area here is located above the reference line. So we have 1/2 48 times 4. This gives us 96 kilonewton meter. So at this point, now take note, this is in the first degree order, so therefore our moment diagram should be in the second degree order. But what would be the curvature or the orientation of our second order curve here? Now take note, our shear diagram is decreasing, so therefore we have our moment diagram here, which is in frowning curvature. Now, if you do not know how to use or how to draw shear and moment diagram, I would refer you to my previous videos discussion on the shear and moment diagram. So I would give you the link in the description below. So if you want to watch it, please just click the link that I provided in the description. So we have 96 kilonewton per meter here. Okay, so we draw a frowning curvature. To compute for the last moment, moment 3, that is the initial moment, 96 kilonewton per meter, plus the area of the shear diagram. Now in this case, this area, this would be the area. Now take note that is negative area since that is below the reference line. So we have minus 1/2 times 48 times the base width, we have 4, and this gives us 0. So again, in order to check whether your shear diagram and moment diagram is correct, if you end with a 0 moment or a 0 shear respectively. Okay, so this one is 0. So that's our moment diagram. Now take note, our maximum moment here is 96 kilonewton per meter. So the critical point in our beam is at the midspan. Okay, because that is where the location of our moment. Okay, so in order to determine the desired cross-section, now we compute for the section modulus. Now we know that we have formula given, which is the flexural stress or the bending stress is equal to the moment over the section modulus, correct? So again, if you were not able to watch my video regarding flexural and bending stresses, so I would provide the link in the description, so please have time to watch them. Okay, now we have FB. Now the moment here is the actual moment, which is 96 kilonewton meter. Okay, so however we convert that into Newton millimeter. So our given FB here is in terms of KSI, that is in 18 kilopound per square inch. So we need to convert it into MPa. Now we have a conversion that 1 KSI is equal to 6.895 megapascal. Okay, so to convert this one, 18 KSI times, now again, 1 KSI is equal to 6.895 megapascal. This would give us 124.11 megapascal. So again, why we need to convert this into MPa, since our values here, our moment, our shear values are in terms of Newton and meter. Okay, so we have 124.11 MPa, or this is 124.11 Newton per square millimeter. So we have our FB, which is 124.11 Newton per square millimeter, is equal to the moment, the maximum moment is 96 times 10 raised to the 6, that is now in Newton millimeter. So I converted kilonewton meter to Newton per millimeter by multiplying 1 million to our value. Okay, so remember the conversion. Now this is over the S. Now this S here, that's the section modulus. Now again, S is equal to the moment of inertia over C. Okay, if you remember that from our previous discussion. So we have our S here, the section modulus. This is the required section modulus, okay, of our beam. We have the required section modulus, which is equal to 773,507 or 773,507, and the unit would be, now take note, you can cancel Newton here, but you cross multiply millimeter squared and millimeter. This would give us millimeter to the third power, or millimeter cube. Okay, so this will be the important data that we will be using in identifying the lightest wide flange shape. Now let's go to our steel table. But before we proceed to the steel table, okay, we look for shape that is a little bit higher, okay, a little bit higher than the required section modulus. Because the higher the section modulus, the greater the cross-sectional area. And we know that the greater cross-sectional area, the higher strength or flexural capacity it would have. Mas safe yung higher ang cross-sectional area. So therefore, in order to choose the economical section, wag yung mas malaki yung cross-sectional area, just a little bit higher than the required cross-sectional area. Now let's go to the SI units, wide flange SI units. So again, I am using Pytel and Cusalaa steel table. This is located at the back of the book. So this one, we have table B-2. This is the wide flange shape. These are the specifications. Now again, we first start from the bottom or the last cross sections of this shape. So we start from the smallest W shape. I guess we have this one. This is the last W shape here. We have W100 by 19.3. So again, you choose the section modulus, which is a little higher compared from the required section modulus. Now again, we have 773, so 773,507 millimeter cube. Now take note, our section modulus here is in terms of 10 cube. Okay, remember this one. This is in terms of 10 cube. So let's start from the bottom. We have we choose 773. Okay, kung meron bang 773 dito. So dito tayo magtingin. So we look at the section modulus column. Now take note, we use XX here since the orientation of our wide flange here is vertically positioned. Our web here is vertically positioned. Okay, so let's go to this part. We have 773 ba? Okay, we have 708. Nope, we should not use this one because this is lesser than the required section modulus. So we choose 852 instead. Okay, so we have our first section here, which is W200 by 86. So we take note of that. So we highlight that one. Then let's proceed now to the other section. We have W250. So we have the next larger section modulus. We have 690, we have 805, so we choose 805. Okay, so we have W250 by 67. Okay, so this is our second identified possible wide flange section. Now in this case, it could be 844. Okay, so we do not choose 747 since this is lesser than 773. Okay, so we choose 844. So we choose the wide flange shape W310 by 60. Okay, next we look on the section modulus column, the S here. Then we go upward. Okay, so we have this value here, we have 773. Okay, however guys, this is lesser than the required section modulus, which is 773.5. However, we can use 926 here, 926, which is higher than the required section modulus. So we can choose wide flange 410 by 53. Okay, then let's go higher, let's go upward. Then we have here 944. Okay, so we have wide flange here 460 by 52, since we have section modulus for this shape, which is higher than the required S. Let's go again upward, but as we noticed, we have higher section modulus na dito. Okay, we have 1,340, 1,870, 3,490, which is the minimum section modulus for each individual shape. So wala na tayong nakikita. So our last section modulus here could be 460 by 52. Okay, so we list down all the possible wide flange shape. Okay, so these are the possible wide flange section that we can use in our beam. Now, which of these sections should be the first one na kailangan nating i-check? Okay, we check each sections here if this exceed the required or the allowable stress, which is 18 KSI or 124.11. Now take note, the actual flexural stress that we should compute here using either of these sections here should be lesser than the allowable stress. Okay, kailangan mas maliit yung actual stress niya. Now looking at the possible wide flange section, which should be the one that we're going to use in our design, okay, or which is the most economical section. Now again, we can check if that section is economical if it has the lightest section among the available wide flange sections here. The lightest here is 360 by 51, since the linear weight is in 51 kilogram per meter. Okay, so this is the lightest among this cross section or among this identified possible economical section. We apply 360 by 51. So use 360 by 51 wide flange shape. Okay, now again, the weight is 51 kilogram per meter. Now in checking if this is safe or not, we should include the weight of that shape in our load diagram. Okay, since we have 51 kilogram per meter, then we should include this in our load diagram. So we convert this one into kilonewton per meter. So we just multiply 51 kilogram times 9.81 meter per square second over meter. This gives us 500.31. When we multiply kilogram and meter per square second, that is in Newton. So therefore, that is in Newton per meter. So we convert this into kilonewton per meter. Then we have 0.5 kilonewton per meter. Okay? So we add this to our original load. So our new load here is the original load, which is 12 kilonewton per meter plus the mass or the linear weight, which is 0.5 kilonewton per meter. So we have our new load here, which is 12.5 kilonewton per meter. So we should not neglect the weight of the beam, because that would be one of the dead loads. Okay, so we compute for the reaction since we have a new load. So the reactions here would be, if we sum up, forces vertical is equal to 0, upward forces are positive. This gives us, let's say this is R1 and this is R2. R1 plus R2 minus 12.5. Now we have the length of this beam, which is equal to 8 meters. Correct? So we have 12.5 times 8 is equal to 0. So we have R1 plus R2 equals 100 kilonewton. Okay? So then we sum up moment, let's say at 2 is equal to 0, counterclockwise positive. So we have negative R1 times 8 minus or plus, since 12.5 kilonewton per meter rotates counterclockwise with respect to 2. So therefore, that is positive. So you have 12.5 times 8, okay, times the distance, okay, which is, since the resultant of our uniformly distributed load is located at midspan, so we have 4 meter distance here. So we have times 4, and this is equal to 0. So we have R1 here, which is equal to 50 kilonewton. So therefore, our R2 here, from this equation, we substitute the value of R1. So this would give us 50 kilonewton as well. Okay? So you have R2 is 50 kilonewton. R1 is 50 kilonewton. So we compute for the maximum moment. So we recompute the maximum moment. And I taught you about area moment method or area method to compute for the maximum moment, okay, which is 96 kilonewton meter for our previous example or our previous diagram. But you can directly compute the maximum moment by using the formula. This is only applicable for this type of beam, for simply supported beam with a uniformly distributed only. Okay, so this is only applicable for this type of beam, which is the maximum moment is WL squared over 8. Okay, let's check it using this one here. Okay, so if we have 12 kilonewton load, 12 kilonewton per meter, the length of the beam is 8 squared over 8. The maximum moment is 96 kilonewton meter. Okay, so therefore, so we have the same answer, either using the area method, the moment equation method, or the direct substitution using the formula WL squared over 8. Okay, now let's go back to our new load diagram here, in which we have 12.5 kilonewton per meter. Okay, so we change, so we have W, which is 12.5 kilonewton per meter times the length 8 squared over 8. We have our maximum moment here, which is equal to 100 kilonewton meter. Okay, now let's compute for the actual bending stress, no, or the actual flexural stress using the W shape that we used or we adapted. So we have, now we know FB actual is equal to the moment actual, or the moment actual, minus the section modulus of the shape that we choose. Okay? So we have FB actual, the flexural stress actual is equal to, now the moment is 100 kilonewton meter, so we change that into Newton per millimeter, or Newton millimeter, by multiplying it by 1 million, or 10 raised to the 6. So we have here Newton millimeter over the section modulus of our chosen shape, which is 360 by 51. The section modulus is 796. This one here, 796 by 796 times 10 raised to the 3. Okay, times 10 raised to the 3. This one is in millimeter cube. So we can cancel out millimeter, and the remaining millimeter in the denominator would be millimeter squared. So we have the actual flexural stress here, which is 125.628 megapascal. This is greater than the required, or the allowable stress, which is 124.11 MPa. So this is not safe. Okay? So what are we going to do? So we choose the next possible section, okay, which is the next lighter section here. Now, after 51, we have 52. Okay, so we use 460 by 52 here. Okay, so this could be, or let's hope that this could be our safest shape. So we use 460 by 52. Okay, and the mass is 52 kilogram per meter. So we convert it again to kilonewton per meter. So we have 52 kilogram times 9.81 meter per square second over a meter. So this is equal to 510.12 Newton per meter, or we have 0.51 kilonewton per meter. Okay, so we add this load here, this weight, to the original load, which is 12 kilonewton per meter. So our new load here is the 12 kilonewton per meter, which is the live load, plus the dead load, which is 0.51 kilonewton per meter. So our load here is equal to 12.51 kilonewton per meter. So that is our new distributed load. So we have R1 and R2. So we go directly with the formula to find the maximum moment. So we have the maximum moment is equal to WL squared over 8. Again, this is only applicable to this type of loading, in which we only have a uniformly distributed load all throughout the simply supported beam. Okay, our W here is 12.51. Our length here is 8. That's the length of the beam. 8 squared over 8. So we have 100.08 kilonewton meters. Okay, so that would be our new maximum moment. So we compute for the actual flexural stress. FB actual is equal to the moment, maximum moment, or the maximum, or the actual moment, over the S of our chosen wide flange section. So we have maximum moment here, 100.08 times 10 raised to the 6, and it is in Newton per Newton millimeter, over the section modulus of the section. We have 460 by 52, we have 944, correct? We have 944 times 10 raised to the 3. Okay, that's in millimeter cube. So our actual here, actual bending stress, or actual flexural stress, which is equal to 106.017, okay, that is in megapascal, and this is lesser than the allowable stress, which is 124.11 MPa. So therefore, this is the safest. Okay, this is safe, and this is the most economical section, or this is the lightest wide flange section, which can be used as the cross section without exceeding the allowable stress. Okay, so this is our final answer. So use wide flange 460 by 52 as your beam cross section. And that's it for the economic section. So if you have question, you can comment it down. I'll try my best to attend all your questions. Thank you guys for listening, and please don't forget to subscribe to my channel. Have a good day.